Thank you for introduction. I'm still Petr Špaček, and I welcome you to Basics of the Benchmarking with a subtitle, Things You Don't Find in a Manual. Jumpstart. Every time someone wants to measure something, I'm tempted to just sit behind the keyboard and start typing in commands immediately, and that's exactly what happened on this slide. So the first bullet point is basically starting bind with the parameter -n1, and that says to start on one CPU thread, so it just only one CPU is used. And the second command is repeating the same query over and over for 5 seconds. So the client tool called DNS-OARC is hammering bind with the same query for 5 seconds, and then it prints out the average number of answers over the period of time. In this case, 24,000 approximately. And then we repeat the same test, but the bind is running on 4 CPU cores, and we get 29,000. Are we done with the benchmarking? Definitely not. If we want meaningful results, like professional measurement, which actually informs us in a way, we really cannot do it with this jumpstart approach, because we've measured something like unknown configuration of the server. We've measured somewhere in an environment we have absolutely no information about, so maybe we have hit an environmental limit, and on the slides there was single number as a result. And that's complete nonsense, because it doesn't tell us anything about the quality of the answers. Maybe all of them were serve-fail, and that's completely useless for the client, but it was fast. So, for professional results, we really have to design the test first, and that very much depends on what we are going to measure, whether it's a DNS resolver, authoritative server, and then we need proper data, because in DNS it's all about the data, and its performance very much depends on the data. Of course, select the right tools for the right job, and test environment validation, that will be a topic for itself. Well, what can I say? Just don't compare apples and pineapples, it doesn't work. So that's the basic principle. We have to know what we are benchmarking and why, and select the right tools. This is practically the most important slide of the presentation. On the left side, you see DNS resolver. On the right side, you see authoritative server. Technically, they have the same input. The DNS packet format is the same for both. Cows and horses feed on grass, same input. But the processing is completely different. The performance is totally different. And obviously, performance measurement methodology for horses and cows has to be different. It's the same for DNS resolvers and authoritative servers. Let's get more technical. On the right side, you see authoritative servers, and typically they have all the data available, quite likely in memory, so with super fast access, below microseconds, super fast. On the left side, you see DNS resolver with a cache, again the same super fast access, typically in memory, but the trouble is that the resolver doesn't have all the data available all the time. So in certain percentage of cases, it has to go over the network link to the authoritative server and back, and that is super slow, like 4 or 5 orders of magnitude slower than the access to the local cache. And while the resolver is waiting for the answer, it has to keep the state. It's like a juggler, basically, keeping the queries in flight and keeping track of them. And that by itself is enough to set resolvers apart from authoritative servers, because the keeping state costs something. It's consuming resources on the resolver side. But it gets much worse, much, much worse. DNS resolver has a cache. That's the reason why it even works in reasonable speed. But the trouble is that if we just stare at the resolver and don't send any packets at all, it's changing its state, because the data in cache have limited lifetime. As time flows, the records are expiring from the cache, so the system under test, the resolver, is changing its state in front of our eyes, even if we don't do anything. And that's a complete nightmare, because one query sent now and the same query sent in 1 second from now and in 10 minutes from now will have different behavior depending on the cache state and cache cleaning and so on. So resolvers are super hard to benchmark. And that brings us to the question of test data. The trouble is that in DNS, different questions look the same, but they have very different processing cost. For resolvers, we just described why. There are like orders of magnitudes differences between different queries depending on state of the cache. But also on the authoritative servers, different query types and different flags in the query and so on also affect the processing cost on the server side. So as a consequence of this, if we want to measure the steady state, the normal operation of a system, we really cannot use a single query as we did in our jumpstart example. We have to use realistic data set, because then with the realistic data set, various queries with different costs average out over time, and we get more realistic result. And then when we are benchmarking resolvers, it's not just about the composition of the queries with different costs, but also about the timing between queries, because it's really important to keep the cache state in sensible state, which matches what would happen in the real deployment. So timing is crucial. For denial of service attacks, it's sort of simpler. We don't have to wait for the attack to happen to record the sample of it and replay it, usually. But we basically need to find the most expensive query for the given implementation and hammer the implementation with the expensive query all the time. That's what attackers typically try to do, unless they are very smart, which is usually not the case. And with that, we've touched on the topic of denial of service attacks. And again, it's more complicated than it seems, because sure, we can benchmark normal operation, we get some number of queries which the server can handle, and then if we want to simulate the denial of service attacks, we have to basically launch the attack, and at the same time, in parallel, have the normal traffic flowing to the server, because the attack might trigger nonlinear behavior in the server. So it's not like 100,000 queries for normal steady state and, I don't know, 900,000 queries for the denial of service. That does not equal 1 million together, because there are nonlinear effects between the two. So it's really important to measure both at the same time and then evaluate what happened with the normal operations. Also, depending on the particular deployment, might be important to measure impact of like management operations. For example, if you are a big hoster and you add and remove DNS zones at the runtime, while the clients are sending queries to you, it's important to try to test this scenario as well, because these like super specialized operations might have also interesting nonlinear effects on the behavior of the server. Okay, we know what we are benchmarking, why, we have the data, we have to select the right tools. There's a lot of information on the table, you don't need to worry about the details, but there are two important pieces. First, for denial of service, normal operation of resolver and normal operation of authoritative servers, there are different tools suitable for these tasks, because the different tools have different algorithms to schedule the packets and how they handle timeouts and so on. So it's important to select the right tool for the specific use case. And second important thing in the table is that even though the manual of the tool tells you that certain features support it, it doesn't mean that it actually works, or that it might work, but it might be using non-realistic algorithm to generate load or handle connection management for TCP or TLS, for example. And if the benchmarking tool is not realistically simulating the behavior of the client, you are of course not getting realistic result. So that's the sad face in the table. In some cases, there are things better avoided in the tools. I have to add that the first column of the table in the PDF slides on web are clickable, so you can get to the website of that given tool to read more. Anyway, let's sum the table up. for a specific use case. For authoritative servers, DNS-perf is like super easy to use. If you've never done any benchmarking, it's easy tool to use. It's maintained by DNS-OARC. It can provide incremental results, like every second partial results. It can give you detailed latency measurement. That's all nice and shiny, except that the tool is not really performant. So it might happen that you will hit performance limit of the DNS-perf itself and not the system under test. On the other side of performance spectrum is a tool called KXDP-GAN. That's part of NoDNS suite, and it has absolutely extreme performance. But it requires support in kernel, in network driver. It's not so easy to use, and it doesn't provide you detailed statistics about latency and so on. So it's harder to use, doesn't have all the features of DNS-perf. So in the end, typically, you end up using both in parallel, DNS-perf for the normal traffic, which is usually not that high volume, and then KXDP-GAN in parallel for the denial of service attacks, and it meets in the same test box in the end. For resolvers, the situation is simpler and more complicated at the same time. In the table, there is a tool called resperf, so the name indicates that, sure, this is the thing for benchmarking resolvers. But it turns out that it's like historical tool, and back then we didn't know better. And the results you get from resperf are completely unrealistic, doesn't tell you anything at all about the real behavior of the resolver. Just don't do it. And if you are after benchmarking DNS resolver realistically in like normal steady state, basically the only option available in the open source land is called DNS Shotgun. And slides, again, have a clickable link which will get you to talk specifically about Shotgun, all the details, how it works and why. And with that, we've designed our test, we have data, we have tools, and we are back to our jumpstart result. We've run bind on one CPU, 4 CPUs, and the increase in throughput was only 20%. So basically the test says that the bind is total scrap. Don't use it. It doesn't scale. Well, we have a hypothesis, and now we have to verify it, right? And the easiest way, if we suspect that the server implementation is a problem, is to use different server. So here, we replace bind with a tool called dumdumd. It's a little echo server written by Jerry from DNS-OARC, and the server doesn't do basically anything. It just accepts a packet and sends it back. No processing whatsoever. So there is no reason why the tool shouldn't scale. We repeat the same measurement on 1 CPU, on 4 CPUs, exactly same tooling, practically same results. So apparently there is some problem. Now, the detective story starts. We look at the server side and the CPU utilization, and we can see that, okay, only one process of dumdumd is running at a time, and it's not even utilizing the CPU fully. So something smells bad here. I'm a networking guy. When I don't know what's happening, I just use TCP dump and stare into it long enough. That's my recipe. So here we run a TCP dump, look at it, and eventually realize that, okay, the source IP address and source port are all the same all the time. And that in practice, because of the architecture of Linux networking stack and so on, causes all the packets to go to the same process on the server side. So that's one obvious problem. Let's fix that. We modify the command line parameters for DNS-perf. We add the -C 128 at the end, and that instructs DNS-perf to use 128 client sockets, or in other words, source ports. Trouble is that it doesn't help at all. It didn't move a needle on the number of answers we receive, but at the same time, TCP dump indicates that it actually works, and it is using more source IP addresses. And on the server side, we actually see that load is now spread among 4 processes, so it did work, but didn't solve the problem. We solved one problem, but apparently not the only one. Well, every advice would be priceless in this situation. For the purposes of these slides, I had 2 virtual machines on 2 different hypervisors connected with real network in between. And just by pure chance, there was a bug in a network driver in the VM. So the version of hypervisor and the VM didn't really work together. Kernel was logging like mad, and we were spitting up error messages in the logs. I have to say that it's not the first time I've encountered buggy network driver. So if you are doing benchmarking, it's really worth trying different versions of the network driver. It's, yeah, pretty wild. Anyway, after upgrading the operating system and network driver with it, we redo the test, run the dumd again on one CPU, run DNS-perf, and we get like 150,000 answers per second. CPU on server is fully utilized. Nice, that's what we would expect from the beginning. Except that when we start dumd on 4 CPUs, we would expect like 4 times increase because it should scale linearly. The echo server doesn't do anything, it just spits the packet back. But we are getting just half of the expected throughput. And for some reason on the server side, the CPU is not really fully utilized. So again, something is wrong here. Maybe if you look at the load distribution on CPUs, we can see that there's like 20% difference between the most and least utilized CPU, and that's kind of a lot, 20%, something is wrong. One theory might be that 128 client sockets is not enough, so it's not, the hashing is not doing a good job, it's not spreading the load. So we change the command line parameters for DNS-perf to DC 256 to use more client sockets, and dash capital T2 uses more threads on the client side just to make sure that the DNS-perf is keeping up. But the trouble is that, again, it didn't help. We are still approximately at half of the expected throughput. So again, there is some other problem, apparently. In the beginning, we thought that the server side is a problem. So we exchanged the server implementation. Here, we might theorize that the client side is a problem. So we use, instead of DNS-perf, the tool called KXDP-GAN. There is an improvement. We are getting to roughly 2/3 of the expected throughput. And on the server side, we can see that the load distribution is more even. So we've actually solved a problem, but again, not the last one. In this very specific case, the trouble was that the server is running in 4 threads, but the network driver was configured with 8 queues. So there was some bottleneck between passing the packets from the network driver to the echo server and back. So we reconfigure the server to use only 4 queues, redo the measurement, and we are getting at like 93% of the expected throughput, more or less, which is pretty nice. On the CPU utilization, we can see that it's almost perfect, but just almost, because 3 out of 4 CPUs are fully utilized, but one has like 5% of spare capacity for some reason. We don't know why. And because we are running out of time, that will be left as a mystery. And here, hopefully, the previous slides convinced you that it's absolutely crucial to basically test the test environment itself. Because if you don't test the test environment, you have no idea whether what you see as a result. Is it actual behavior of the server, or is it like, you know, firewall table overflowing, or what it is? And let me reiterate that the resolvers and authoritative servers are completely different beasts. That's the most important part of this presentation, really. You have to adapt the methodology to the problem at hand. It's like, if you compare authoritative servers, it's like the racing horses, right? You organize a horse race, that's proper methodology for testing authoritative servers or horses. But if you put a cow to the horse race, obviously you are not getting anything useful. It will be fun, but totally informative. And again, denial of service attacks and normal operations have nonlinear effects. You have to benchmark both. And with that, we are really out of time. So for evaluating the results, please have a look at the talk at previous OARCs where we go into details, not the measurement itself, but how to interpret the results, what it can mean, and what to look at except just number of answers. Thank you for your time and attention.
Thanks, Petr. Excellent talk. Wes Hardiker, USC ISI, and the ICANN board, not speaking for the ICANN board. I have a master's student that ran into exactly this problem. It's like, how do we manage to test things? And getting the load on the server to hit 100% was a real challenge. One of the things that he found was, throwing more threads at it and throwing more clients at it, like you sort of indicated, really helps. But there's a limit. You can actually graph at some point. You start adding too many, and then you're actually decreasing, the throughput again. And finding that sweet spot took him a little while. So, did you look at that sort of the tailing end too and notice a similar result?
I will generalize your observation that basically the takeaway is that almost everything is non-linear behavior. Even if you think that it must be linear, it's not.
Yep. Thank you.
Okay, a couple of questions from the chat. First, from Petr Mansik. He says, I love those icons. Where do they come from?
I think it's Noto font. It's just emojis, Noto font. Grammatic.
Also a question from Puneet Sood. Can any of these tools run in a controller/worker mode and use multiple machines?
None of the tools listed in the table, that's like the layer on top. When we do benchmarking at scale, we have like Ansible or some other orchestration which runs the tools in parallel and gathers the partial results and combines them together. Thank you.